Well, in developing the understanding about this behavior of systems governed by a set of differential equations, we had taken a specific route. It was that when you have a set of differential equations x dot is equal to f of x, then it gives essentially the state space where x and y are the coordinates, where x vector is x y. Now, every point here would be, every state is just a point in the state space, and whenever you say that, this equation defines a vector. So, at every point in the state space there will be a vector, and the solution will essentially follow these set of vectors. Okay, that was the logic, and then we extended that to formulate the methods of solving the differential equations numerically. But when we come to the analytical solution or developing an analytical understanding, we said that let us not consider the whole space and the vectors in it in one go. Let us treat the problem in stages, where we first treat what happens in the neighborhood of some special points. These are the equilibrium points where x dot is equal to 0. That means, these points have the property that if this is the point, then if the initial condition is there, it will forever remain there. So, we said that we first let us understand the character of the system in the neighborhood of that. So, in the neighborhood of such points, we had locally linearized it by obtaining the Jacobian matrix. So, ultimately we had obtained the equations of this form. Say if it is 2D, then it would be x dot y dot is equal to some matrix times x y, square matrix with 4 terms here. So, this will be the Jacobian matrix. This we have seen that. And then we said that okay, if this is the set of equations on which we are further developing the concept, then our state space is where this is the equilibrium point. That means, the equilibrium point essentially has been moved by the coordinate transformation into the origin. So, you have this nu x and this nu y, which are actually the deviations from the equilibrium point if it is placed somewhere else. So, keep that in mind. So, these are the new x and y when seen just in the neighborhood of that equilibrium point, and then the equations governing it would be x dot y dot is equal to this x and y. Then we said that if that is so, then the character of the system, the evolution of any initial condition, say it starts from here, how it goes, all that will then be given by just this matrix, because there is nothing else in the system. So, this matrix will contain all the information necessary in order to understand the dynamics of the system. So, how? Then we said okay, we have a method of solving differential equations for 1D systems, which is if you have simply one dimensional system, x dot is equal to some Ax, then the solution was x at t was x naught e to the power a t. We know this. Somehow we want to use this in order to obtain the solution of this differential equation. But then we had said that we will use the property that if you can somehow obtain two solutions, then any solution would be a linear combination of those solutions. So, what or how to obtain these two solutions was the problem that we were considering in the last class. And then we said that in this space you have x and y space, we have some spatial directions that have the property, say this is the one direction, say, and this is another direction. So, that have the property that if any initial condition is placed there, that means if your x vector x, sorry, I'll draw it with the capital X. The x vector, if it is here, then x dot is equal to a times x. So, this is the vector, this is the operator which is operating on x, is giving x dot, that will also be in the same direction. That means like this. These special directions we said are called the eigen directions. Any vector along an eigen direction is eigenvector, and in that case what happens is, if it is in the same direction, you can say that x dot is equal to nothing but a number multiplied by the old vector x. This number is the eigenvalue. Okay. And then we in the last class we had understood how to obtain the eigenvalues and eigenvectors. Then the crucial point is that if an initial condition starts on an eigenvector, that means an initial condition is placed on an eigenvector, the x dot vector will be in the same direction, and therefore, it will move in the same direction. If it is, if the x dot is in the opposite direction, it will still move in the same direction, in the opposite direction, all right, but in the same, along the same line, along the same eigen direction, which means that if an initial condition is here or anywhere on this eigen direction, it will forever remain confined to that eigen direction, which means this is a one dimensional equation, it will effectively become a one dimensional system. If it is a one dimensional system, then we can use this solution that we have already obtained. Now, there will be one such solution then obtained along this direction, another such solution obtained along that direction, and therefore, any given solution will be nothing but a linear combination of these two solutions. So, that was the simple logic that we are proceeding with. So, is the method of obtaining the eigenvalues or eigenvectors clear in the last class? Okay, we will do examples, so it will be more practiced. So, from here we take off. Now, suppose your eigen direction is say V1 and say V2, these are the two eigen directions, and the eigen value along this is say lambda 1 and the eigen value along this is say lambda 2. So, associated with each eigen direction there will be one eigen value. Now, suppose you have placed an initial condition here, which means our x is V1. In that case, we will write that x is then V1. So, x dot is equal to A into V1. Now, since this is on the eigen direction, therefore, your equation actually reduces to lambda 1 V1. Okay. So, what is the solution of this? X dot is equal to lambda 1, this is a number, times V1. What is the solution of this? X1 of t is equal to fine. So, it will be V1 times e to the power lambda 1 t, right. For a solution, for a initial condition that is placed along this, the solution will be following this, that is one of the solutions, right. Similarly, if you place another initial condition on this, so this is for an initial condition on V1. V1 is the eigen direction. Then the for an initial condition placed on V 2, it will be x 2 of t is equal to V 2 e to the power lambda 2 t. These two are two possible solutions. The moment we have obtained this, any solution will be just a linear combination of this. So, any solution will then be simply x of t is equal to some C 1 constant times V 1 e to the power lambda 1 t plus C 2 V 2 e to the power lambda 2 t. Okay. Normally, C 1 is a number, this is also a number, but this is a vector. So, if I want to distinguish between the numbers and the vectors, I should better put some kind of a symbol, meaning that these are vectors. So, x t is equal to, this is the vector, this is the vector, or normally one would like to write it as e to the power lambda 1 t times the vector v 1 plus c 2 e to the power lambda 2 t times v 2. Fine. Let us just do an example. What does this mean? Okay, we'll understand that after we work out the example. Suppose you have an equation given as x dot y dot, which is nothing but x dot x vector is equal to minus 4, minus 3, 2 and 3 x and y. What will you do? We will first obtain the eigenvalues and eigenvectors of this matrix. Just obtain it. You know how to. We will say A, this matrix, minus lambda I, its determinant is equal to 0. A minus lambda I would be A minus 4 minus lambda minus 3, 2, 3 minus lambda equal to 0, minus 4 minus lambda, 3 minus lambda plus 6 is equal to 0. Just obtain the eigenvalues from here, minus 3 and 2. Okay. So, lambda is equal to, there are two things, 2 and minus 3. So, these are the two eigenvalues. So, we will say that here in this picture the two eigenvalues are 2 and minus 3. Now, let us obtain the corresponding eigenvectors. So, let us, in order to do that, we will first start with the value 2. So, for lambda 1 is equal to 2, what will you write? The matrix A minus lambda I is equal to 0, which will say sorry, A minus lambda I x is equal to 0. So, from there you obtain it. What are the two vectors? So, this is the matrix A minus lambda I substitute 2, it is minus 4, minus 2, this is minus 6, this is minus 3, 2. So, it will be minus 6, minus 3, 2 and 1, x y is equal to 0. You will see the first equation is minus 6 x minus 3 y is equal to 0, and the second equation is twice x plus y is equal to 0. They are actually the same. So, what does it say? The equation is wait, the eigen direction. Here it is the eigen direction, not the eigen vector. It will give the eigen direction. It says that the eigen direction is where twice x is equal to minus y. In order to place an initial condition on that eigen direction, you have to a priori specify some value of x and then find out the y value of y. Say x is equal to 1, then y is equal to, this gives y is equal to minus 2. So, the vector for eigenvalue 2, the eigenvector is what? 1 and minus 2, right. Similarly, obtain the other eigenvector for minus 3. Tell me what it is. In the same way, for eigenvalue minus 3, eigenvector is depends on where you have placed the initial condition, minus 3 1 or 1 minus 3, same thing really, depends on where you have placed the eigenvector. What I am trying to mean is that minus 3 1 is not sacrosanct, it could be just anything, clear, that is important. So, if one of you say that no, it is minus 3 1 and the fellow says no 3 minus 1, fine, so long as it is in the same eigenvector. So, let us take one of them, 3 minus 1 maybe, check that it is on the same eigenvector, fine, okay. Just to make sure, since you have said it is 1 minus 3, I say no, 3 minus 1, because it is the same eigenvector. Now, you have to write it like this, which means we can say that x of t, which is x t by t, is equal to C 1 e to the power twice t times this eigenvector plus C 2 e to the power minus 3 t times this eigenvector. Fine. Which means it is actually, if you write it in individual equation form, x of t is equal to C 1 e to the power twice t plus C 2 into 3 e to the power minus 3 t, okay, and y t is C 1 minus I will write it correctly, minus 2 minus twice C 1 e to the power twice t plus minus C 2 e to the power minus 3 t, right. So, these are the individual equations, but we would prefer to write it as the vector equation like this, because of some conceptual clarity. I will come to that. So, where do you get the C 1 and C 2 from? From the initial condition. So, just calculate that once for say for the initial condition. Can you calculate the values of C 1 and C 2? What will you write? These two initial condition mean t is 0. So, x and y at 0 is 1 1. So, you will say 1 is equal to C 1 e to the power twice 0, this is 1, okay. So, C 1 plus C 2 thrice C 2 and 1 is equal to minus 2 C 1 minus C 2. 2 equations, 2 unknowns, solve it and get it. What do you have? This will give C 1 is equal to what? Just do that. Minus 4 by 5. Okay. And C 2 is okay, which means the actual equation, if you have this as a starting point, would be simply this. So, it will be x vector of t is equal to C 1 is minus 4 by 5 e to the power twice t 1 minus 2 plus C 2 is 3 by 5 e to the power minus thrice t 3 and minus 1. That will be the solution. Fine. Obtaining such a solution is not a very difficult thing, but what I am trying to drive at is that gives a very nice geometric way of looking at things. What is happening? You have the state space like this with x and y are the coordinates. Okay. Now, where is this vector? 1 minus 2, 1 minus 2. So, it should be something like this. That is the eigen direction physically. This is 3 minus 1. So, go to 3 and slight bit here. So, it will be, I will draw it a different, okay, I will draw it later. So, for the eigenvector, that is 1 minus 2, your associated eigenvalue is 2. So, with this you have 2 and with this you have minus 3. Fine. Clear? Now, then this one, any initial condition along this, say like this, will increase as e to the power twice t, it will increase, while any initial condition on this will go as e to the power minus 3 t, it will decrease exponentially. So, anything here will go out, anything here will go in. Fine. So, is that clear? In general, I will come to the cases where the other points are also to be marked. For example, if you start from this initial condition, that initial condition, I will come to a little later, but let us understand the situation where both the eigen directions have negative eigenvalues, because this is a case where one eigenvalue was positive, another negative, but let us consider the situation with negative eigenvalues. Then suppose you have an eigenvector like this, another eigenvector like that, and suppose the associated eigenvalues here are say minus 1 and say minus 3. Try to figure out how the behavior will be. After all, the behavior will be something like this, only thing is that here in place of 2 it will be minus 1. My point is then the equation would be of this form, which means that if you ignore this, it will be an exponentially decaying value. If you ignore this, it will be exponentially decaying value. So, start from here, it will be exponentially decaying, start from here, it will be exponentially decaying. So, I will put arrows like this. Make it clear. Why? Because if you start from an initial condition say here, its evolution will be governed by the initial condition times say I will say x. So, x times e to the power minus 1 t. This minus 1 t is a exponentially decaying function, therefore, this magnitude will go down and down and down, finally, it will converge. That is why I put the arrow like this. Now, suppose you have started an initial condition somewhere here. What will its behavior be? Try to figure out on the basis of this kind of equation. So, the equation would be of this form: x of t is C1 e to the power lambda 1 t V1 plus C2 e to the power lambda 2 t V2. These two are the eigenvectors. Notice that the ultimate solution is a linear combination of these two solutions, which means that effectively these two solutions evolve independently and the ultimate solution is just the addition of them, which means if you drop such parallels, then you will find that the initial deviation from the origin along this eigen direction is this much, and that will evolve as this. Initial deviation along the other eigen direction is this much, it will evolve as that. Fine. This has a relatively larger eigenvalue minus 1 and this has a relatively smaller eigenvalue minus 2. So, which one will decay faster? This term will decay faster. This term is along that. So, it will decay faster along that and relatively slower along that. What does it mean? What will be the evolution like? It will be like this. Okay. Did I really solve equations? No. From logic we could infer that the behavior would be like this. Is that clear? So, depending on the relative magnitudes of the eigenvalues, if they are both negative, then it will converge all right, but it will converge always after converging first on along after converge first to one of the eigen directions. It will not just converge just like this, no. It will first converge on one of the eigenvectors and then along that it will finally converge on the fixed point, equilibrium point. Clear? Ultimately, if you draw individually this and that, you will find both will be like this. You will actually like to see the evolutions along x and y, they will both be like that, all right. So, just by looking at this, you do not see that it is actually converging onto an eigen direction and then meeting the fixed point, but it will always do so. Okay. If you start from another initial condition, say here, it will, what will it do? How? How? This will have this as the initial deviation, this as the initial deviation. Which one will decay faster? This one will decay faster. So, as a result, it will converge onto this first, and then it will start from here, it will converge like this. Start from here, it will converge. Start from here. Okay. So, can you see that without ever doing anything else, I am drawing the vector field just by working out logically that this will have the behavior like this. This is the vector field. So, the vector field around the equilibrium point, if the two eigenvalues happen to be minus 1 and minus 3, should be something like this. And this I did not work out simply by computer, but this can be worked out by logic. So, you see, if both the eigenvalues are real and negative, then the behavior will be always like this. if you have the two eigendirections drawn, then it will be oh no, I have crossed this eigendirection, sorry, it is wrong. It will be fine, it will be like that, provided this has an eigenvalue -1, this has an eigenvalue -3, or this is larger than this. What if both the eigenvalues are positive and real? It will be just the opposite, only the arrow heads will be in the other side, right, only the arrow heads will be the other side. So, if okay, probably you have noticed that I said that this is wrong. Why did I say it is wrong? Because it will never cross an eigendirection. So, that is one of the important points. The vector fields will never cross the eigendirections. Vector fields will always, in this direction it will be just like this, in this direction it will be just like that. What we have effectively done is to imagine a coordinate transformation where we have called this as the new x coordinate, that as the new y coordinate, then it's simple. Okay, when if both the eigenvalues are real and positive, then it is just the opposite it will be fine. So, if you start an initial condition very close to the equilibrium point, it will go out, all right. If you have initial condition exactly at the equilibrium point, it will stay there. Slight perturbation, then it will first start off along an eigenvector and then go away in the other direction. It will always start off along parallel to tangentially to one of the eigenvectors, and then it will go away. Okay, suppose this is okay, that is a good question. Out of this, which one has a greater eigenvalue? The way I have drawn it. Imagine you have taken a point, it has two projections, and in this case, this one is increasing faster, that is why it is fast going this way, which means this has this particular direction has. So, say it is say 3 and this is say 1. Is that clear? Fine. I did not really write down the equations for this, can be inferred from logic. Now, let us come to the case that we started with eigenvalues 1 and -3, right. This had to be understood a little later, that is why I first came through this and then talked about this. Fine. Now, you have say two eigendirections like this, and say this fellow has eigenvalue 1 and this fellow has eigenvalue -3. Then what will be the behavior? Notice that any initial condition along that will do what? It will grow. So, start from here, it will grow. I will have to draw the arrows like this. I will have to draw the arrows like that. Along this, anything will evolve as e to the power minus 3 t. So, along this it will be e to the power minus 3 t, along that it will be e to the power 1 t. So, it will be decaying. So, I will have to put arrows like that. Start from initial condition somewhere else, say here. What will be the behavior like? Again, imagine in terms of the two projections and how the projections evolve. Because ultimately your x of t is c1 e to the power lambda 1 t v1 plus c2 e to the power lambda 2 t v2. So, the projections, this v1 or this v1 and the v2 are the components along the two eigen directions. Consider them separately, because they are actually evolving separately. So, this is the component along this eigen direction which decays, and this is the component along this eigen direction that increases. So, the behavior will be right. Start from any initial condition here, what will it do? Again along this it will decay, along that it will grow. So, it will be start from initial condition, say here, along this it will decay, along that it will grow, and initial condition here it will go like this. So, do you see the structure of the vectors? And if you want to visualize the vector field, draw a few more of these lines, it will be easier then to visualize. So, that is how. So, any initial condition, its component along these directions will reduce, along these directions will grow. It is somewhat like the behavior if you release a marble on say a saddle, then saddle means the saddle on the top of a horse is something like this, right. If you release a marble somewhere here, it will stay there, but if you start from somewhere here, it will roll back. If you give a slight perturbation this way, it will roll down. So, the behavior of anything placed on a saddle is similar to here. You see, this perturbation is similar to this perturbation along this line, and this perturbation is similar to this perturbation along that line. That is why such equilibrium points are called saddles. So, this is called a saddle. And saddle equilibrium point. The situations where situations like this are called nodes. Situations, that means this equilibrium point is called a node, where the vector field lines converge. This is where vector field lines are converging, so it will be called a stable node. In this case, the vector field lines are emerging from there and going outwards. It will also be called a node, but it will be an unstable node. It is also called a repeller, because any initial condition here is repelled away. So, this is a stable node, or it is also called an attractor, because any initial condition is attracted to this point. Any initial condition will be attracted to this point. Good. So far so good, there is no problem. We have understood the cases where there are real eigenvalues. Now the troublesome case, the complex eigenvalues. We have to understand that also. How to do, what to do with complex eigenvalues. Okay. Obviously, the eigenvalues are obtained from a quadratic equation solution. So, that will be lambda is equal to some kind of minus b plus minus root over b square minus 4 a c by twice a. This term, depending on the b square minus 4 a c, it could as well be negative or positive. If it is negative, you will a complex number. But notice that it is not just a complex number, but always complex conjugate. Do you know why? Can it yield just one complex value? Why not? At least not this, but say a higher dimensional system where this would not be quadratic, say cubic, quintic, whatever. Yes, if the polynomial coefficients are real, then there is a theorem proved very long back, probably by D. Alembert, that if the polynomial coefficients are real, then it will either yield real eigenvalues or complex conjugate eigenvalues. It can never be a single complex value. So, it is always be complex conjugate. If they are complex conjugate, then if, see, what was our logic? Our logic is that we will try to identify one direction in which we will place an initial condition, we will obtain a possible solution, another direction along which I will place another initial condition, I will get a possible solution. But now we have trouble because these two, it is, if one is p plus jq, the other is p minus jq, right, which means that they do not have any independent information. Okay. The information that is contained in one, the same information is contained in the other fellow, which is a conjugate. So, they cannot give two independent directions. That is one trouble, but we will overcome this trouble. That is not a big problem as such. So, you have say an eigenvalue, that is lambda 1, which is complex. There will of course be another lambda 2, which is lambda 1 bar complex conjugate. Now, the next stage was that we had to identify the eigenvector and then place an initial condition on that eigenvector. Now, what the hell the eigenvector is in this case? Okay. That is obviously a question, because if you have a complex number, the eigenvector will also be a complex eigenvector. What do you mean by complex eigenvector? Normally, we were writing the vector like 1, minus 3, this is a real vector, while a complex vector might be 1 plus j, 3 minus j, something like this, that is all. A vector in which the individual elements are complex numbers. But still the question remains, in a real space, real valued space, I can draw the direction of the eigenvector. What is this? Obviously, this is not any real direction in the real valued state space. So, how do you visualize then? Wait, patience, because the way to visualize would be that still this equation is valid, x 1 dot is equal to A x was the equation, that is equal to lambda x if the initial condition is along the eigenvector, right. What is the meaning of the term if the initial condition is along the eigenvector? Obviously, it is not a physical vector, but still I will clarify that. But if that is true, then the solution is x is equal to times the eigenvector v, okay, along the eigenvector I will say v. So, if the initial condition is along the eigenvector v, then this is true, this is then v lambda v, x dot is equal to lambda v, and then the solution is this. Good. Let's figure out this solution. Lambda is a complex number, v is a complex thing. So, this solution is also a complex number. What do you mean by a complex number as a solution? Now, this left hand side is definitely real, fine. Why? Because it is the solution of this equation. X is a real thing, A is a real thing, x dot is a real thing. So, this has to be real. This tells us that the state goes from here to here, and therefore, that must be real number. So, this is real, but this is a complex. Good. So, there is a problem. No, that is not a big problem, because this can always be expressed as P plus jq. If that be expressed, then notice that this is a linear combination of a vector p, real vector p, and a real vector q. So, this is a linear combination of real vectors p and q. So, x, a solution, is a linear combination of the real vector p and the real vector q, which means the p and q must individually be solutions, right. So, one solution, sorry, p, other solution, the moment you have two real solutions, you can always construct any solution out of these this combination. Let us see. So, what was the logic? Again, let us recapitulate or reiterate with the logic that I was proposing. What I am saying is that if you have a complex valued eigenvalue and complex value is complex conjugate, their eigenvectors will also be complex conjugate. There is no point using both the eigenvalues. Why? Because they carry no new information. So, just take one of them, say lambda 1. Obtain the corresponding eigenvector. How will you come to obtain the corresponding complex eigenvector? I will come to, I will show you, not a problem. Obtain the corresponding eigenvector. The moment you have obtained the corresponding eigenvector, you can write an equation like this, because you know the vector, you know the eigenvalue, and therefore, you know the solution. That solution will consist of, the solution will be a complex valued solution that can be broken into a real part and an imaginary part with j multiplied. So, this term is a real valued thing. Take them separately, they will definitely be two separate linearly independent solutions, and then construct the final solution out of these two. Okay. Logic wise, at least I know everybody is somewhat initially have some kind of discomfiture with this kind of situation, because I cannot visualize the vector. Real things are nice, because you know the vector, I have got a component here, it decays, it grows, what is this? Yes, but at least there is no flaw in this logic. Go with this logic, let us see. If there is somebody who is not convinced with this logic, I can take you through another logic also. For example, suppose you have two solutions, two eigenvalues which are say lambda 1 and lambda 2. Lambda 1 is equal to say sigma plus j omega, sorry, lambda 1, and then lambda 2 must be sigma minus j omega. Okay. For this, the eigen vector is say v, then for this the eigenvector must be v bar, which is the complex conjugate part of it, which is the complex conjugate part of it. So, you have v and v bar and lambda 1 and lambda 2. So, the final solution is definitely x of t will be C1 then e to the power sigma plus j omega times v plus t plus C2 e to the power sigma minus j omega t v bar. Okay. Now, C1 plus C1 and C2, these things again have to be obtained from the initial conditions, that is what we have done. But then in this kind of a setting, the C1 and C2 will also be complex. C1 and C2 will also be complex. And not only that, these two terms will also be complex conjugate. So, if you actually do the algebra, you will find that these two terms will always be complex conjugate. So, ultimately what you have is x of t will become what I mean to say is that it is breakable into two parts, one with the real part of this plus the real part of that, another with the imaginary part of this and the imaginary part of that. It is breakable into two components. They will be twice the real part of C1 v e to the power sigma plus j omega t. Okay. Fine. So, that will be the value here, and there can be another part constructed out of so this already contains this. So, you have this component which is the real part and the imaginary part. These can be separated out into a complete real part plus j into a complete imaginary part, and these two individually will become the solutions. That is the logic. So, in the earlier logic we were not considering both the eigenvalues and eigenvectors, but if you do consider, then also it leads to the same result. In the next day we will illustrate this with an example, where you will actually derive the solution. We will continue with that in the next class.